Okay, good morning everyone, and thank you, the organisers, for inviting me, and thank you for turning up at 9 o'clock in the morning to come and hear what I've got to say. So I'm going to talk today about hard and soft elasticity of polydomain liquid crystal elastomers. This work really pertains to my PhD work, which was supervised by Mark Warner, who's in the room, and a special thanks to Mark. And so, without further ado, I'm going to start my story at the beginning. So, what's a liquid crystal elastomer? So we learned in Antonio's talk yesterday, right, so we all know what a liquid crystal is. It's a liquid crystal conference. We all understand that if we put our liquid crystal rods, we can attach them to long polymer chains, either as pendants or as part of the backbone to make a liquid crystal polymer. And then the final step in this sequence of ideas is we can then take a liquid crystal polymer and we can introduce cross-links between the polymer chains to make a solid matrix, a soft solid, with a liquid crystal phase embedded inside it, and that's a liquid crystal elastomer. So it's a liquid crystal phase that lives inside a soft solid. The key idea here is that the liquid crystal phase, you continue to see the same transitions between the different phases as you did in the liquid state, but now they couple to the shape of the solid. So the key phenomenon from which everything else comes is that at high temperatures, your soft solid takes on an isotropic configuration with no liquid crystal order inside it, and then you cool, and the rods form into a nematic phase, and along the direction in which the nematic phase is pointing, there is a large stretch, a large shape change. So there's a picture here, which I have stolen from Eugene Terenchev's website. So this is hot, and then cold, and then hot again, and then cold again. So when you cool to the nematic phase, you get an alignment of the liquid crystal rods, and this is coupled with a really large spontaneous distortion. But, as I'm sure, so I think as Tom originally pointed out, right, there's something a bit fishy about this because the hot isotropic state was, to the name, isotropic. So when you cooled, so I said you cooled and it popped out looking like this, you had a big spontaneous distortion in this direction, but because this state is isotropic, there's no good reason why you didn't see this, or anything else in between. And consequently, if you take this state, you can deform it around this ring into this state. And it's important to realize that these two are not related by rotation, they really are rotated by a mechanical stretch, a real shape change. That's a bit more obvious if you imagine the intermediate state. But nonetheless, the rods can rotate, and this change in shape can be accommodated without any additional energy being paid. So although we notionally have a solid, in fact it's a solid which can sustain very large shape changes at essentially no energetic cost. So this soft elasticity, which is related to this broken symmetry, is really the most interesting thing I would say about these elastomers. And does it really happen? So this is an experiment. So this is a sample with the order all in this direction, and then if you imagine it's pulled horizontally. And what you can see is that as you pull it horizontally, it stretches and stretches and stretches, with this stress against strain. So it stretches at very, very low stress until you reach a point like this, where the rods are all pointing in the order along the stress direction. And then once the rotation is complete, the stress picks up in a big way, because now you're really stretching the rubber backbone rather than just accommodating it by rotating the liquid crystal order. So, so it has a real clear physical signature. How would we think about modeling this? So what I want to think about now is some state given here, which is the state in which I cross-linked, and then I'm going to apply some deformation or some displacement field u to get a state in after deformation. I've done a cross-link in the presence of some liquid crystal order given by Q naught. And then this state is parameterized by some coordinate capital X, and this state is coordinated by some coordinate little x, which is of course a function of big X. So the shape change between these two states is best described by the deformation gradient, which is just d little x by d big X, which is really, that just tells you if is it a rotation, is it a stretch, is it a shear, or whatever. And then the energy I would expect to write in a form like this, So it has a sum really of three components. R is for rubber, that's the energy coming from the polymer chains, which we might expect to depend on how much we've changed their shape, what the liquid crystal order was in the final state, and what the liquid crystal order was when we cross-linked. This is F Landau de Gennes, and this is just a liquid crystal energy, which depends on Q. In particular, it really depends on the magnitude of Q. There's no anisotropy here. So this is the part of the energy which is going to incentivize the liquid crystal rods to align. And then we've got a Frank energy, which depends on spatial gradients of Q, which penalizes gradients in Q. Okay, I'm at this stage going to immediately get rid of this one. I'm going to think about structures where there isn't, for the time being, any gradients, spatial gradients of Q. So we ignore this. And then we're going to think about the relative size of these two. So this one has order kBt per rod. This one has order kBt per chain. And there are many liquid crystalline rods for each chain. And so this is much bigger. So consequently, when I minimize this energy over magnitudes of Q, that's really a process dominated by this part of the energy. And therefore, going forwards, I'm going to forget also this part of the energy and rather replace this by a constraint which just says the magnitude of Q is fixed. And so all we're going to have left is my polymer part of the energy, but modulo the consideration that because we know about these other parts, the magnitude of Q is no longer a free variable, but the direction of the pneumatic order is still something which can couple to the rubber elasticity. Okay, so we've reduced our problem from 3 compartments just to 1. If it was just a simple rubber, okay, we know from microscopic or phenomenological reasons that we would expect an answer that looked like the trace of lambda times lambda transpose, or if you prefer to think about that in terms of the principal stretches of lambda, that's lambda 1 squared plus lambda 2 squared plus lambda 3 squared. This is the so-called near-Hookean energy, which works for, for Gaussian rubber, so if you have relatively dilute crosslinks and long polymer chains. And so how does this get affected? So I'm going to start about this. So if you attack the problem in the same way microscopically, but in the presence of liquid crystal order, you end up with this expression here, which is, so this was, Antonio called this the trace formula in his talk yesterday. And what you see is it bears a strong resemblance to the previous result, but now in addition to, inside this trace, as well as the lambda and lambda transpose, there are these tensors L0 and L to the minus 1. Okay, so L0 records the liquid crystal order when you cross-linked, and L to the minus 1 is a reflection of the liquid crystal order in the final state. They're L's, not Q's, that's for 2 reasons. The first is simply that Q reflects the pneumatic order, but these reflect not the pneumatic order, but the coupling between the pneumatic order and the polymers. So, so if there was no coupling, these would have to disappear, even though Q hadn't disappeared. And secondly, because, again, if there was no coupling, these disappearing means going to identity, not going to naught. So in fact, L then is a simple uniaxial tensor. It just points along N, which is the liquid crystal direction. So in its diagonal frame, it really is, just 1, 1, and then some anisotropy. And then, of course, L0 is fixed for all time. Right? The direction in which L0 points was fixed at cross-linking. The direction in which L points depends on the final state liquid crystal director. So it can point in any direction. Okay, now, so the reason I've gone down a little bit of detail is, so this is really, I would say, you get this microscopically. And you get quite a big result when you do this, because it's not at all evident that this should have a soft mode. And the reason I would say it's not at all evident is because this L0 is here, and this L0 looks like a permanent record of where the director was when you cross-linked, and therefore there's no reason why trying to rotate the director away from that direction should be soft. And in fact, I think it's not at all clear why that would be true. Also, though, we've written the energy in some sense in a counterintuitive way, because we've written the energy as if we cross-linked in a state like this. And so if you imagine deforming this state, okay, although we know going round this circle ought to be soft, right, it's only when we write with respect to this state that we get to really see that symmetry obviously. So what we're going to try and do then is, rather than write with respect to deformations from this cross-linking state, to return back to the isotropic state and write our deformations with respect to that state. And what we hope we're going to see is that when we do that, suddenly this symmetry structure becomes obvious and the soft mode appears. To do that, okay, we make this change of variables. So little lambda recorded the deformation from the aligned state. We're going to write this as capital lambda, which is the deformation from that isotropic state. And then L0 to the minus a half is, it turns out, the deformation you need to transform between those two states. And what you can see is if you put this into here just algebraically, all record of L0 disappears. And you end up with this energy here. And this is an important microscopic result, right, which says that even if you cross-link in the pneumatic state, where on symmetry grounds you didn't have a reasonable expectation where soft mode should exist, in fact there is still an isotropic reference state you can write everything with respect from. You still see the full symmetry structure, you still see the soft mode. So you don't destroy it if you cross-link in the pneumatic state. Okay, one final point. So, okay, I've now got my energy written like this. I've gone back to deformations from the isotropic state. I don't really get to choose the director. Right, the director will be chosen by minimizing the energy, so I should really minimize this energy over choices of director. So, okay, so I want to minimize this energy over all the directions the director could point in. When I do that, okay, that's minimizing the directions L can point in, and it's going to be minimized by L being codiagonal with lambda lambda transpose. Okay, and so what basically happens here is this minimization says that the liquid crystal director should point along the direction of largest stretch of lambda. That's the energy minimizing thing to do, and when you do that, you get to lambda 1 squared plus lambda 2 squared plus lambda 3 squared over r. So very similar to the near-Hookean case, only this 1 over r is the new thing. And what this is saying is that you don't pay as much for the largest stretch in your system as you were expecting. So you pay less by a factor of 1 over r. And then, okay, if you minimize this then over lambdas, it's minimized by any lambda which has the structure that it's a stretch of power of r to the 1/3 in some direction. So any lambda which is a stretch of r to the 1/3 in any direction, okay, you will put the liquid crystal director in that direction, and then that's an energy minimizer of the system. So we've recovered then our soft mode. Okay, so just to recap, we're writing then now from this state, and we're heading out a stretch of r to the 1/3 in this direction gives this low energy state, a stretch of r to the 1/3 in this direction gives this low energy state, and so on and so forth. Okay, so far so good, but it's clearly not quite true. In particular, it's not quite true because this stress isn't literally zero. So if this symmetry argument absolutely stood up, you might have hoped you could reorient from here to here without paying any energy whatsoever, and that's okay, it's low, but it's not literally zero. And with a related problem here, right, we might know either experimentally because we've played with kinematics in the lab, or theoretically because we've read about Imrie and Marr and Larkin, that if we had some disorder in this, we would expect rather to get not a nice monodomain where all the liquid crystal directors point in the same direction throughout, but rather a polydomain structure. So what is driving all of the liquid crystal rods throughout the sample to all point in the vertical direction? Why is it that in some areas they don't point in one direction and in some areas another direction? In other words, so it's clear why we have local order from this energy, but we might expect a polydomain structure where globally it was isotropic. Now, okay, so we know from liquid crystal liquids that we normally get these defect structures, which are certainly globally isotropic. And so sure enough, if you prepare your liquid crystal elastomer without due care and attention, you end up with a polydomain structure consisting of lots of little domains with liquid crystal order pointing in different directions, and consequently no macroscopic shape change when you go through the phase transition, because all the little phase changes are in, all the shape changes of domains are in different directions, and they in some sense cancel out. And the question we want to address is this going to be hard or soft? If I try and pull this, say in the horizontal direction, do I expect hard or soft response? There are two ways to think about this, and they give contradictory answers, right? One is that if I pull this in the horizontal direction, this domain here is already oriented in the horizontal direction, so when I pull, it must respond in a hard way. It has no possibility to offer direct rotation to make a soft mode. Okay, therefore it should be hard. One is to say, but there are domains like this which are perpendicular to the stress direction, and these can rotate towards the stress direction, and that should be soft, and therefore the response should be soft. And it's unclear which of these two ideas is the right one. We'll just say then, so then polydomains, how would we have made a monodomain? We would have made a monodomain, in fact, by imprinting some direction on the material. Now, we've agreed that you can't really do that just by cross-linking in the nematic state, but you could apply a big magnetic field or a big stress field or some such during the cross-linking process to weakly make one direction globally a slightly preferred direction. And then all the domains would know that, okay, although they were basically soft and most directions had nearly the same energy, there is one direction which is slightly preferred, and they all agree globally on this energy because we imprinted it at cross-linking. So I would say one final point about this, right? There is a very good energy to describe this. This is originally in microscopic configurations, although I would think about this phenomenologically. But okay, this is basically the old part of the energy. This is the part with the complete soft mode, and then plus alpha, plus a term which has some n naughts in it, which are an imprinted preferred direction. So this part is completely soft. This part, proportional to alpha, which we expect to be a small number, gives you a weak preference to line up your director along n naught. Okay, and what I'm going to say, because I'm going to use it later, right, is this energy actually works really well. Okay, these theoretical lines in stress-strain, and this is actually direct rotation, I think, is a function of strain. You know, it gives really good answers for the monodomain samples. Okay, so here's a fundamental question. Polydomains, hard or soft? Now, so as Yuriyama told us yesterday, and as in fact Ukido in the audience anticipated several years before we got to this problem, the answer depends on how you cross-link the sample. So the important point is if you have an isotropic liquid and you cross-link it and then you cool to a nematic state, you get a polydomain which responds in a completely soft way. If you cool to a nematic polydomain liquid and then you cross-link it, you get a solid which behaves in a completely hard way. And so I hope I'm going to try and explain to you, I'll give you no, this is actually not very complicated. I think there's a simple reason why this is true. So first of all, how are we going to model a polydomain? Okay, so that's why I spent quite a long time trying to motivate with energy. We're going to use exactly the same energy we use for monodomain. The only difference now is that this weakly imprinted direction here is going to become a function of position. Okay, so I'm going to use exactly the same energy. I'm basically saying that each domain locally is a very small monodomain. Only this imprinted direction is now a function of space. And that's going to hopefully incentivize the polydomain structure. Okay, so that's how I'm going to do this. So actually, before we do that, let's just take a step back. So I'm going to imagine first the, in some sense, ideal polydomain, where this term isn't there, so there is no imprinting. And let's just ask what would happen in that case. And so the key insight, which I think explains why, if you cross-link in the isotropic state, you get a completely soft macroscopic response, is as follows. So we've now we're dealing with the perfect energy. So the energy is minimized by a distortion of magnitude r to the 1/3 in any direction, okay? So an elongation in any direction, and then you put, of the right magnitude, and then you put the liquid crystal director along that direction, gives you an energy minima. So here we imagine something in the isotropic state. So if I cool it, and it tries to make a domain structure that looks like this. Okay, so one oriented like this and correspondingly stretched in this direction, and then one oriented horizontally and correspondingly stretched in the horizontal direction. Okay, that's very bad, because although individually these domains are completely happy, they've stretched along their director by the right amount, okay, this boundary has ripped, or at the very least become extremely stressed, and that's not good. Okay, there's definitely going to be a very strong energy penalty associated with that. So this is a domain structure which one cannot observe if you cross-link in the isotropic and then cool under the constraint that you remain a solid. Here, on the other hand, is an example of a domain structure which, from this kind of continuity perspective, is allowed. Okay, so here, the two domains have popped up, and the boundary bisects the two normals, and therefore has been equally stretched on both sides, so they match. And therefore, there is no mismatch of strain across this boundary, no build-up of stress, no tearing. So cooling under the condition of being a solid places a very harsh constraint on what kind of domains can form. So now, the really important thing here is you say, okay, so if I'm forgetting that alpha term, forgetting that anchoring term, and I just have the big term, okay, then one definite possibility is that by happenstance, every single domain chooses to align in the same direction. That's definitely kinematically compatible. Okay, it will result in the solid macroscopically extending, and it's definitely a low energy state because each part elastomer has extended by r to the 1/3. So if I didn't have that anchoring terms, then in fact the state where it fully aligns and therefore stretches with respect to the isotropic parent state globally is definitely a low energy state. So I'm trying to show some picture here. So here we have my isotropic state, and then we cool it. Now what happens here I'll drop in a minute. What's clear is if we stretch it out so that all the domains are aligned, if we only have this part of the energy, the real symmetry broken part of the energy, this should be a low energy state. The miracle actually is not that this is a low energy state, it's that it manages to find a state like this. Okay, so it manages to find a state where macroscopically it doesn't change shape, but microscopically everywhere it is extended by r to the 1/3 in some direction. So that there is some nice compatible domain structure which gives no global shape change, but makes everything locally happy. So I would say, so the mystery is not that this is low energy actually, it's that this state exists at all. However, this is only half a mystery because it was solved by Antonio. So this is the same energy you would use to model a monodomain. And he said, if this energy is all you've got, I can ask the question, if I put my system in a box, what is the energy minimizing domain structure? And what he showed was that there are indeed, he gave examples of domain structures which result in no macroscopic shape change, but result in all the microscopic domains being energetically low. So energetically, they were stretching r to 1/3 in some direction, so they're low energy. He showed that these states do exist. The structures he had to use to show that are rather complicated. They involve laminates inside laminates, 2 layers of length scale separation. And I'm not sure at all clear that's going to be physically realized in the material. But nonetheless, in principle, such strain fields do exist. And not only do they exist all the way from getting from here and all the intermediate states to getting to here. So if we have just this part of the energy, we have a situation like this. So now this is now my free energy as a function of stretch from that isotropic state. So this is the kind of raw free energy, which says that only when you stretch by r to the 1/3 do you get to the low energy state. Okay, and then this blue line is the energy you get after you have allowed for the possibility of the most favourable domain structure inside the sample. And what you see is that it's as good as it possibly could be. It's completely flat all the way out to r to the 1/3, and then, okay, further stretching at that state does start to cost you energy. Okay, so this is the energy if the microscopic deformation was really the same as the macroscopic deformation, and this is the energy after you allow the formation of the most favourable domain structure. Okay, and then this is energy against stretch. Clearly, if I take a derivative, I get stress, and this is stress-free. So you get a stress-free transition from from macroscopically isotropic to macroscopically aligned. Okay, so now we should try and put some disorder back into this system. So here we have it. Here's the big part of the energy, again, written from the isotropic reference state. This is the part we've been treating so far, and then plus alpha, which we're hoping is going to be small, plus some energy that gives it a weak incentive to prefer n0 at a given location. And n0 is going to be a function of x. So this part we saw actually was completely degenerate. Like, this didn't care whether it was perfectly aligned or in the complicated domain structure. This part hopefully is going to incentivize the complicated domain structure, so it explains why we don't see any spontaneous state change when we just cool it, and we do have to do a little bit of work to stretch it out. Now, this is very hard to do anything sensible with, principally because I haven't been willing to say anything about the structure of this n0 field. So the form we'll probably want to look at now, sorry, this lambda here should be a capital lambda. Right, okay, we want to take this energy, we want to integrate it over the volume of the elastomer, subject to the boundary condition that we've got some displacement on the boundary, and then we need to minimize it over all internal displacements. Okay, so subject to capital lambda being a gradient of a displacement field, so being a kinematically compatible displacement, and we also need to minimize over all n of x. Okay, and now this is basically an incredibly difficult problem, again, not least because I haven't at this point given you an explicit n of x, n0 of x with this imprinted field. So we're going to take two simple approaches to try and say something about this. We're going to try and bound it from below and above. To bound it from below, I'm going to throw out this gradient thing. Okay, so this gradient thing says that the deformation better be the gradient of a displacement field. If I throw out that constraint and minimize over all deformations, I'm minimizing over a wider function class, so I get a lower answer. And again, if you throw that out, then you get an easy minimization here. So we get a lower bound by minimizing over, by really throwing out this kinematic compatibility constraint and minimizing over all deformations, subject only to the average deformation being what you thought. Then for an upper bound, we forget the minimization altogether, and instead we throw into this energy just an example of a strain field and evaluate that energy. And that certainly gives you an answer that's bigger than this object. So, okay, and then so where do we get these test strain fields from? So there are, of course, you can choose anything, but the ones that we use, which gave fairly good answers, is to use the test strain fields, which are the domain structures posited by Antonio, which minimize this part perfectly. Okay, and then you just evaluate their energy with this part. So we choose the domain structures which minimize the dominant part of the energy completely. And it's easy to evaluate how much energy penalty they incur from this part, because these domain structures don't correlate with n0 at all. So assuming almost nothing about n0 other than that it's isotropic and random, you can work out the averages there very easily. When you do that, you get some quite tight bounds. So it's important to realize why these bounds are tight, right? These bounds are tight because if alpha was 0, I would have that perfect energy, and I know the perfect answer. So I'm only really putting bounds on that small addition to the energy, and therefore I end up with bounds that are pretty tight. This blue line is the upper bound. This red line is that lower bound, where I've thrown out kinematic compatibility. The green line is an even lower bound, where I set alpha to 0. Okay, so these are bounds on the energy. To move from bounds on energy to bounds on stress-strain, you need to put in the additional idea that the energy curve had better be convex. So then you can ask at any point in here, if I'm here and I know I'm on a convex curve, what's the steepest my energy curve could possibly be? And therefore, what's the minimum and maximum stress that could possibly be at that point? So you can take that to get a pair of stress bounds. So the blue and green are stress bounds derived from its energy bounds. The red line is literally the derivative of the lower bound, which is an estimate rather than anything rigorous. And these dots here are Uriyama's data. Where is he? Thank you. And you see, it works reasonably well. And in particular, you do see this big soft transition until it's fully oriented, and then once it's fully oriented, it kicks off in a hard way. Okay, so this then, so what I'm trying to say here, let's get the most important point here. The most important point here is that if you have crossing at the isotopic state, you're completely soft. And that's really because actually you've got a monodomain. Right? The large dominant part of the energy doesn't have any spatial dependence. And in fact, these are probably closer to being monodomains than the things that in the field have been called monodomains. Right? The spatial dependence and the inbuilt, the inbuilt anchoring of the director is weaker. Now, suppose we do the opposite. Suppose we cool our liquid to a nematic state, and then we cross-link. So now all bets are off, right? So now there is nothing that says you can't have one domain like this and one domain like this, because they nestled up like that next to each other in a liquid when there was no constraint of kinematic compatibility, and then you turned it into a solid. So even though these states still have perfectly soft local modes, they can't realize them, because if you imagine trying to stretch an ensemble like this, this one, I'm stretching in the horizontal direction. This one cannot stretch softly at all because its director is already aligned in the horizontal direction. This one could stretch softly, but when it stretches softly in the horizontal direction, it must get thinner in the vertical direction, and that's going to cause problems on the boundary. Again, stress at an energy penalty. So the real point here then is that here you get a pattern of domains chosen by the nematic liquid, and there's no good reason why that should be a kinematically compatible structure. And indeed, the condition of being kinematically compatible is an extremely strong condition. So in fact, it absolutely certainly won't be. Okay, so you might complain I've drawn pathological cases here with really sharp domain boundaries, which is not something a liquid would do. But the nice, smooth versions you would see in a liquid are just as bad. That's a little bit harder to see they're bad. Okay, so this is then the basic intuition, right? The domain structure was chosen in the liquid state, and therefore we don't get any possibility of cooperation between the domains. And in fact, the idea here then is we don't even need, probably, any anchoring part of this energy to explain why these things have a hard response. Right? Even if we assume these local domains are absolutely perfectly soft, they have no personal domain preference to point this way rather than this way. Okay, they still can't get away from their original state without paying energy penalty because really of geometric frustration, right? They can't do it because this one cannot deform softly without requiring this one to deform as well. Okay, so they're geometrically constrained. So even if I put in a perfectly soft local energy, my expectation is that this is going to be hard. Now, I'm saying expectation quite carefully. Okay, I should say, so this is the energy you now use. So this is the energy you get. The perfectly soft energy if you cross-link with some order n L0 in the digital state. And then the idea is now this L0 should now follow a typical nematic liquid defect pattern. I say I expect. I actually don't know how to prove this. If I try and do my same lower bound and upper bound trick, the upper bound actually works perfectly well. The lower bound, as we discussed, I arrived at by throwing out the condition of kinematic compatibility and minimizing over a wider function class. But if we believe it's kinematic compatibility that's preventing it being completely soft, then throwing that out means you lose the effect. So in fact, okay, so this is a quite embarrassing set of bounds. This one, however, all I will say is that the upper bound, so given a nice test strain field, if you take the derivative of that, you do indeed get something that matches experimental data rather well. I'd be very interested if anyone has a good idea how to incorporate the constraint of kinematic compatibility to give me a better lower bound. The one thing that is clear there is if you want to do that, you're going to have to say something more about the domain structure. Sorry, yes?
Go back to the previous slide. So why in the nematic state do you have directors that go?
Oh, sorry, so this is a particularly pathological example. I'm not claiming this is what happens. Rather, what I'm claiming is that the set of domains which would be able to be soft macroscopically is an extremely special set of states. And there's no reason why the nematic liquid would have chosen one of those states. So maybe I should have drawn some more smoother nematic liquid-looking things, but you would run into exactly the same problem, because the set of states which... So the question you should ask really is, if I go to the high temperature state, okay, then this one wants to contract in this direction, and this one wants to contract in this direction. So you'll get the global soft mode if you can get to a nice high temperature state. And what you see is here you can't, because, okay, again, this one contracts like this, and this one contracts like this, and the boundary doesn't complains. Whereas you're guaranteed you can do that in the isotropic genesis case because you cross-linked in it, and so you know it exists. Sorry,
I
you're...
guess I'm really confused about something stupid. If I'm in the nematic phase and it's equilibrium, N naught doesn't depend on X, does it?
Oh, so N naught depends, so if I have a nematic liquid, okay, for sure, if I wait long enough, I think it does turn into a real monodomain. But at any finite time, it has a wonderful disclination pattern in it. And then when I cross-link in, that's what appears.
So I see. So you're doing it in an inhomogeneous nematic as opposed
Oh, yes, oh, no. So if you start with a perfectly oriented nematic phase, then you're absolutely right. But then you haven't got a polydomain at all, I think. Then you have something that starts with long-range order. OK, so here's the quick summary. If you cross-link in the isotropic state, you have a locally soft mode and a macroscopically soft mode. You have a domain structure that's driven by kinematic compatibility, which we expect to be qualitatively a different structure to that seen in a normal nematic liquid. And there's certainly no internal stress in the high-temperature state, because that's where you cross-linked. And so we know with a stress-free configuration for that state. If you cross-link in the nematic state, it's locally soft. Okay, the domains locally have a soft mode, but macroscopically they're completely hard. The domain structure is inherited from the nematic liquid, and therefore looks like that from a nematic liquid, not that something driven by kinematic compatibility. And there is internal stress in the high-temperature state, because you can't make that transformation back globally. A couple more points. So the isotropic genesis polydomains, what I really want to say here is that these really are, in terms of if you write down the energy function, the biggest part of the energy function doesn't have any spatial dependence. The biggest part of the energy function, therefore, is the monodomain energy. And therefore, I think there's a strong argument that actually these should get a lot more attention. They're easier to make than monodomains. They're mechanically probably even softer. Okay, because they start from this macroscopically isotropic state, rather than having very special soft deformations, in fact, all small volume preserving deformations will be soft. We saw in Uriyama's talk yesterday that they can be electrically actuated. We've seen previously they can be light actuated. I will just point out they can also be temperature actuated. Like this is a sort of silly example, but you can imagine here is my isotropic genesis polydomain. I stick a weight on the end, and it stretches out into a monodomain. Very small weight, because that's basically a soft deformation. But then for sure, if I heat it up, then it will contract back to its isotropic state. And I can cool it and it will do it. So we even get this big, quote-unquote, global spontaneous distortion. And in fact, I think, really honestly, truthfully, like this system here of a polydomain with a weight on the end is going to have exactly the same theory as the monodomain theory we've developed previously in the area. OK, a few more points. We're at the tip of the iceberg here. Once you realize that the state you cross-link in and the state you cool to can be arbitrary, and it matters, there's a huge richness here, because you can cross-link, okay, you can cross-link in the isotropic state, or a nematic monodomain state, or a nematic polydomain state, and on and on and on. Right? Any liquid crystal you choose, you can have, and you can have it in a disturbed state, which is macroscopic isotropic, or one with global order, and then you can cross-link, and you can cool to more or less anything else, or indeed heat up. So you could think about a sort of polydomain, right? You could take which is a nematic polydomain cross-linked, and then heat it to an isotropic state. So there's an enormous amount of structure here, which I think no one has thought about, the vast majority of these, certainly not made any. There are two that I'll flag up, as I think might be particularly interesting, one theoretically and one experimentally. So symmetric A monodomain, cross-linking state, and then cooling to a symmetric C state. I think this has potential to be a very good electrical actuator, for a reason I'll just mention in a moment. And symmetric A polydomain state, cross-link and then cool to a symmetric C state, I think has, well, so it's mathematically analogous to a Martensite polycrystal. And maybe if I have time, I'll say something about that in a moment. So let me just try and motivate both of these. Also, because I hope this will bring together the basic idea from the nematic case. Okay, so if you have a symmetric case, okay, you know that symmetric liquid crystals are layered. And if it's symmetric A, it all points like this. And then if you have it in the solid and you cool from symmetric A to symmetric C, then okay, the rods tilt relative to the layer normal, and that's accompanied by a shear. That's the kind of mechanical consequence in the elastomer context. And okay, so this shear could happen in either direction, or indeed, honestly, it could happen on a cone, right? So this is a different continuous symmetry that's been broken, and therefore there's a soft mode associated with that shear angle. So if you start with the symmetric A monodomain, and then you cool without any further constraints, different parts of it will choose different symmetric C order. And so you will get a polydomain symmetric C order inside a symmetric A monodomain order, but exactly the same idea as before, right? So it's possible that every domain could have accidentally chosen this configuration or this configuration, and in terms of the dominant part of the energy, the non-disordered part of the energy, that will be a minima. And therefore, you will end up with something that looks roughly this shape, but you can shear it yourself all the way from here or all the way to here, and that will be basically soft. The reason I'm saying that, okay, so that first of all illustrates the general point. I think the general guidance on these is if you cross-link in the high symmetry state, so if you cross-link in a state which has macroscopic symmetry, and then you break the symmetry once you're a solid, you recover a macroscopic soft mode. If you don't, you don't. And secondly, okay, symmetric Cs can be ferroelectric, and therefore, if you're looking for something you might want to actuate electrically, the expectation is this will be extremely soft because it's a polydomain, and it will couple very well to the electric field because it's ferroelectric. So in fact, you should be able to drive the transition from this to this, and then from this to this, via electric field. And that might be a good candidate for a rather low field actuator. Okay, so that one I suspect might be experimentally interesting. This one, I want to say something about it possibly being, so this is now, so martensites have a very analogous system. Okay, in a martensite, you have a metal which lives on a lattice, and then you cool it, and your lattice undergoes a phase transition which breaks a discrete symmetry. Okay, so here, a very simple possible case, you've got a square lattice and you cool it, and it makes a rectangular lattice in one of two different ways. And therefore, it has a soft mode because you can turn this lattice into this lattice for zero energy cost. So it's a very analogous system, except that now the symmetry you've broken is discrete rather than continuous. And indeed, much of the work to do with textures and domain structures, which I've talked about earlier, I think originally was inspired by work in the martensite community. So there's a big analogy between martensites and liquid crystal elastomers. And I was expecting when I started out on this work that liquid crystal elastomer polydomains would be directly analogous to martensite polycrystals. But that turns out absolutely not to be true. So a martensite polycrystal, what they mean when they talk about this, is a system which, in the high temperature, high symmetry state, is already a polycrystal. So it has some crystal grains that have this, but then somewhere later there'll be another part of the crystal where it'll still be a square lattice, but it'll be in some completely different configuration. So what they mean by a polycrystal is something which has a high temperature state with this high symmetry, but the symmetry is different in different places. Like the lattice has different orientations in different places. And then you cool, and you break this phase, you get the soft mode once you're already in the polycrystal state. And there's sometimes when you do this, you get a global soft mode, sometimes you don't. This is completely different to what we did, because in our system, we had an isotropic. Our high symmetry was completely isotropic, and therefore there was no real sense in which it could point in a different direction in one place or another, because it's isotropic, so there isn't any scope for doing that. Symmetric A to symmetric C is different, though. Symmetric A to symmetric C, you really can do this, because you can imagine a symmetric A polydomain, which is like the high symmetry polydomain, right? It's the high symmetry state because I'm going to move to symmetric C, but it's polydomain because it can point in all sorts of different spaces, even in the liquid. And then I cool to symmetric C, and I break the symmetry at each point, and then you get something that really is mathematically analogous to a polycrystal in the martensite literature. And whether that's going to be hard or soft, that's the one I really don't know, actually. Sometimes in martensite, these things turn out to be hard, sometimes they turn out to be soft. So the rule for the rest of them, I think, is if you have a global symmetry in the cross-linking state, and then you cool to a lower symmetry state, you'll get a global soft mode. This case, I'm not sure. Okay, questions. There are several big questions here. I'm going to jump the gun here. You can ask me any of these questions, but don't expect a good answer. Okay, what really is the domain structure of isotropic polydomains? Okay, de Simone's construction involving two layers of separation of length scales doesn't look real. Also, we know from Riemann-style arguments that the breaking of the long-range order should involve continuous changes in the director field, but all the positive domain structures have these sharp boundaries, because that's what the massive kinematic compatibility tends to be written in terms of. So I think there's a big question, both experimentally and theoretically, as to what the actual shape of these things is. Okay, what is the source and strength of disorder? Well, the strong suggestion is probably the crosslinks, but that's definitely not clear. And then can we make a microscopic model that moves from the source and strength of disorder to predicting how macroscopically hard these things are? So I've just posited a strength completely arbitrarily, really, to match the data. Can we say something microscopic about that? Can we engineer them to be even softer by understanding the source of that? how do we prove that the nematic polydomains are actually hard? Okay, that's probably more of a personal problem than for everyone else, but it upsets me. And then finally, take-home messages. Okay, this is where it gets ever slightly more controversial. What I really want to say, okay, so the engineers, polydomains can be softer, can actuate just as well, and are easier to make. So I think there's good reason to think they might have an engineering future. For everyone, there are many unexplored phases. We've really only done the tip of the iceberg. So, like I say, I've talked about symmetric A polydomains and symmetric A to symmetric C polydomains, but there are really n-squared combinations in there, and there's a lot of richness that might come out. And then finally, even for the simplest cases, even for this isotropic genesis nematic polydomain, there are some really serious theoretical questions which I certainly don't know how to answer. So, okay, that's my final slide. Thank you for listening.
Thank you. Questions?
On the isotropic genesis case,
Yes.
what was the assumption on the N0 field?
So
N0, the preferred director, N0, N naught.
Oh, what was the, sorry. So the question, I think, is, so in my, oh, no, wrong one. Sorry, let me go back. Okay, so in my isotropic cross-linking case, I said there's this big, properly soft energy, which doesn't have any spatial dependence because I cross-linked in the isotropic state, and then we have plus a small term which encodes some preference for a local director. And the question is, how did I choose the size of that term, I think? So how did I choose the prefactor here? And the answer to that is very simple. I fit it to the data.
So
I have no microscopic understanding of how big that term is.
How about the spatial structure of the field, N0?
Again, I said nothing. So the bounds I made are bounds that are completely independent of the structure of N0.
Okay, so
they require only that it be macroscopically isotropic and random. So it's a big enough sample that it is macroscopically isotropic and that there aren't long-range correlations in it. So I didn't say anything more than that.
Okay, so you say that it does not depend
On the what, sorry?
correlation length of the N0 is not important for your result.
The correlation length?
Correlation
length. No. So indeed. Right, because I worked by putting in test strain fields, which didn't know anything about N0, all I needed to do to work out the energy was to assume that N0 averaged to 0, and didn't correlate at all with my underlying domain structures. I didn't need to say anything more than that. That's not to say these aren't excellent questions. These are really the important questions, but they're not questions I've got any answers to.
Okay, I should discuss it with you.
Thank you. Other questions?
Yes. I was wondering, how would you model the symmetric liquid crystal elastomer? It seems that a possibility for, well, I'm just wondering that you would need an order parameter and that perhaps you would have some sort of a Chen-Lubensky type. Would it be an additive term?
I think, in the interest of time, I'm going to dodge that question and say that James later, I think, is giving an entire talk on this subject.
Okay, then we have a question.
Okay, so I have two comments and a question. So comment, I think you should call the nematic genesis polymers defected nematic genesis.
Defect, okay.
Because otherwise we get confused as I did. Also for the comparison between the martensites and the smectics, that I think it's unlikely you're going to get the random rotation of the smectic actually. You'll get focal conics and things like that, which are likely to have the same problem as the defected nematic. In other words, tendency to be hard rather than soft.
So I guess the point I was trying to make is because you break the symmetry after you've put that in, they will. I don't know whether the respect A to respect C transition is self-accommodating, right? But when you go through that transition, it might locally make some complicated texture pattern, in some sense, on a much smaller scale. So you get a region where the symmetric A was effectively homogeneous. But on the transition, you'll get a much finer domain structure driven by kinematic compatibility.
I see. I thought you were making the comparison between the martensite that was rendered random in the square state.
Oh, no. So I am, and of course you are. I don't know how random the martensite polycrystals are like that.
Well, it's polycrystal,
but certainly
with
you're-
more or
yes.
less arbitrary orientations.
Okay, yes. So, there'll be so you're saying there'll be much more structure in the symmetric A state. I think that's certainly true.
And the final question is, you know, there's an old problem in magnets. If you have a random anisotropy magnet, you get a kind of a spin glass,
Yes.
which to my knowledge has never been totally thought out. So have you thought about applying this kind of analysis to a magnet? So you know,
I think
a magnet that can point anywhere in space. and
no,
then you have
I know
anisotropy
exactly what
atoms.
you mean, and I don't know. I guess having learned as a very small person that was a terribly difficult problem, I've never dared try and think about it.
I think it may be similar. You might want to look at it.
But maybe I should.
Thank you very much again.
Thank you.